Chapter 7 Graph 1. Graphs extremely useful tool in modeling problems consist of vertices, edges. AEFDCB vertex edge vertices can be considered sites or locations. Edges represent connections. 2. Applications air flight system. Each vertex represents a city. Each edge represents a direct flight between two cities. A query on direct flights becomes a query on whether an edge exists. A query on how to get to a location is, does a path exist from A to B? We can even associate costs to edges, weighted graphs, then ask what is the cheapest path from A to B. 3. Another application, wireless communication, can be represented by a weighted complete graph. Every two vertices are connected by an edge. Each edge represents the Euclidean distance edge between two stations. Each station uses a certain power I to transmit messages. Given this power I, only a few nodes can be reached, bold edges. A station reachable by I then use its own power to relay the message to other stations not reachable by I. A typical wireless communication problem is how to broadcast between all stations such that they are all connected and the power consumption is minimized. 4. Definition: indirect graph. An indirect graph is specified by unordered pair, VE, where V is the set of vertices and EE set of pairs of vertices, represents edges BECFEFABACBDCD5. Terminology: 1. If 1 and 2 are connected, they are said to be adjacent vertices. V1 and 2 are endpoints of the edge V1 V2 2. If an edge EA is connected to, then V is said to be incidentone. Also, the edge EA is said to be incidentin. 3. Degree of deg V to be the number of edges incident to. 4. In indirect graph, V1 V2 equals V2 V1 asterisk asterisk. Later, we will talk about directed graphs, where edges have direction. This means that V1 V2 is not equal to V2 V1. Directed graphs are drawn with arrows, called arcs, between edges. AB. This means AB only, not BA6. Graph representation. Two popular computer representations of a graph. Both represent the vertex set and the edge set, but in different ways. One adjacency matrix use a 2D matrix to represent the graph. Two adjacency list use a 1D array of linked lists. 7. Adjacency matrix 2D array A0 N1 0 N1. Where n is the number of vertices in the graph. Each row and column is indexed by the vertex ID, e.g. A equals 0, B equals 1, C equals 2, D equals 3, E equals 4. An array entry Aij is equal to 1 if there is an edge connecting vertices I and j, otherwise, Aij is 0. The storage requirement is n2. Not efficient if the graph has few edges. We can detect in O1 time whether two vertices are connected. 8. Adjacency list. The adjacency list is an array A0 N1 of lists, where n is the number of vertices in the graph. Each array entry is indexed by the vertex ID, as with adjacency matrix. The list AI stores the IDs of the vertices adjacent to it. 9. Examples: 4 1 5 0 2 3 6 8 7 9 0 1 2 3 4 5 6 7 8 9 0 0 0 0 0 0 1 0 0 0 0 0 1 0 1 0 0 0 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 Examples for 150236879012345678981618111029237914814523365 Storage of adjacency list. The array takes up n space defined degree of deg v to be the number of edges incident to. Then, the total space to store the graph is proportional to deg v vertex v and edge E equals uv of the graph contributes a count of 1 to deg, u, and contributes a count 1 to deg, v, therefore sigma vertex deg, v, equals 2m, where m is the total number of edges in all, the adjacency list takes up, n plus m, space. If m equals O, n2, both adjacent matrix and adjacent lists use, n2, space. If m equals O, n, adjacent list outperform adjacent matrix. However, one cannot tell in O, 1, time whether two vertices are connected. 12. Adjacency lists versus matrix. Adjacency lists more compact than adjacency matrices. If graph has few edges, requires more time to find if an edge exists. Adjacency matrix always require n2 space. This can waste a lot of space if the number of edges Aries parse. Can quickly find if an edge exists. 13. Path between vertices. A path is a sequence of vertices, v0, v1, v2, vk, such that, for 0 less than or equal to iltk, vi plus 1 is an edge. For 0 less than or equal to iltk1, vi is not equal to vi plus 2, that is, the edge vi plus 1 is not equal to vi plus 1, vi plus 2. Note, a path is allowed to go through the same vertex or the same edge any number of times. The length of a path is the number of edges on the path. 14. Types of paths. A path is simple if and only if it does not contain a vertex more than once. A path is a cycle if and only if 0 equals vk, the beginning and end are the same vertex. A path contains a cycle if some vertex appears twice or more. 15. Examples. 1. ACFE2, ABDCFE3, A, C, D, B, D, C, F, E4, ACDBA5, ACFEBDCA. Are these paths? Any cycles? What is the path's length? 16. Graph traversal application. Example given a graph representation and a vertex synthegraph. Find all paths from to other vertices. Two common graph traversal algorithms. Breadth first search, BFS, find the shortest paths in an unweighted graph. Depth first search, DFS, topological sort. Find strongly connected components. Let's first look at BFS 17. 129S1152, BFS and shortest path problem. Given any source vertexes, BFS visits the other vertices at increasing distance SOWD from S. In doing so, BFS discovers paths from S to other vertices. What do we mean by distance? The number of edges on a path from S082. Example, consider S equals vertex 1 nodes at distance 1, 2, 3, 7, 9 nodes at distance 2, 8, 6, 5, 4 nodes at distance 3, 0, 1, 3, 4, 18, 2, 6, 2, 7, 1. BSF algorithm. Y use Q. Need FIFO 19. Example adjacency list visited table, T/F, 1587960 F1 F2 F3 F4 F5 F6 F7 F8 F9 F243 source 0 initialize visited table, all false, Q equals initialize to be empty 20. Example adjacency list visited table, T/F, 1587960 F1 F2 T3 F4 F5 F6 F7 F8 F9 F3420 flag that 2 has been visited. Q equals 2 place source 2 on the Q. 21 source. Example adjacency list visited table, T/F, 81759 neighbors 60 F1 T2 T3 F4 T5 F6 F7 F8 T9 F marked neighbors as visited. 3420 Q equals 2 rightward arrow 8, 1, 4 deq 2. Place all visited neighbors of 2 on the Q22 source. Example adjacency list visited table, T/F, 819756 neighbors 0 T1 T2 T3 F4 T5 F6 F7 F8 T9 T marked new visited neighbors. Source 2430 Q equals 8, 1, 4 rightward arrow 1, 4, 0, 9 deq 8. Place all unvisited neighbors of 8 on the queue. 23. Notice that 2 is not placed on the queue again, it has been visited. Example adjacency list visited table, T/F, 89715 neighbors 60 T1 T2 T3 T4 T5 F6 F7 T8 T9 T mark new visited neighbors. 24 source 30 Q equals 1, 4, 0, 9 rightward arrow 4, 0, 9, 3, 7 decu 1. Place all unvisited neighbors of 1 on the queue. 24 only nodes 3 and 7 haven't been visited yet. Example adjacency list visited table, T/F, 15879 neighbors 60 T1 T2 T3 T4 T5 F6 F7 T8 T9 T source 2430 Q equals 4, 0, 9, 3, 7 rightward arrow 0, 9, 3, 7 decu 4. 4 has no unvisited neighbors. 25. Example adjacency list visited table, T/F, 15879 neighbors 60 T1 T2 T3 T4 T5 F6 F7 T8 T9 T source 2430 Q equals 0, 9, 3, 7 rightward arrow 9, 3, 7 decu 0. 0 has no unvisited neighbors. 26. Example adjacency list visited table, T/F, 15896 neighbors 0 T1 T2 T3 T4 T5 F6 F7 T8 T9 T243 source 0 Q equals 9, 3, 7 rightward arrow 3, 7 decu 9. 9 has no unvisited neighbors. 27. Example adjacency list visited table, T/F, 15879 neighbors 60 T1 T2 T3 T4 T5 T6 F7 T8 T9 T mark new visited vertex 5. 24 source 30 Q equals 3, 7 rightward arrow 7, 5 decu 3. Place neighbor 5 on the queue. 28. Example adjacency list visited table, T/F, 15897 neighbors 60 T1 T2 T3 T4 T5 T6 T7 T8 T9 T mark new visited vertex 6. 243 source 0 Q equals 7, 5 rightward arrow 5, 6 decu 7. Place neighbor 6 on the queue. 29. Example adjacency list visited table, T/F, 15879 neighbors 60 T1 T2 T3 T4 T5 T6 T7 T8 T9 T243 source 0 Q equals 5, 6 rightward arrow 6 decu 5. No unvisited neighbors of 5. 30. Example adjacency list visited table, T/F, 15879 neighbors 60 T1 T2 T3 T4 T5 T6 T7 T8 T9 T243 source 0 Q equals 6 rightward arrow decu 6. No unvisited neighbors of 6. 31. Example adjacency list visited table, T/F, 1587960 T1 T2 T3 T4 T5 T6 T7 T8 T9 T243 source 0 Q equals what did we discover? Look at visited tables. Stop. Q is empty. There exists a path from source vertex 2 to all vertices in the graph. 32. Time complexity of BFS, using adjacency list. Assume adjacency list n equals number of vertices m equals number of edges O, n plus m. Each vertex will enter Q at most once. Each iteration takes time proportional to deg, v, plus 1. The number 1 is to include the case where deg, v, equals 0. 33. Running time given a graph with m edges, what is the total degree? Sigma vertex deg, v, equals 2m. The total running time of the while loop is, O, sigma vertex, deg, v, plus 1, equals O, n plus m. This is summing over all the iterations in the while loop. 34. Time complexity of BFS, using adjacency matrix. Assume adjacency list n equals number of vertices m equals number of edges O, n2. Finding the adjacent vertices of B requires checking all elements in the row. This takes linear time O, n. Summing over all the n iterations, the total running time is O, n2. So, with adjacency matrix, BFS is O, n2, independent of number of edges m. With adjacent lists, BFS is O, n plus m, if 35m equals O, n2, like a dense graph, O, n plus m, equals O, n2. Shortest path recording BFS we saw only tells us whether a path exists from source S to other vertices V. It doesn't tell us the path. We need to modify the algorithm to record the path. How can we do that? Note, we do not know which vertices lie on this path until we reach V. Efficient solution: use an additional array pred 0 and 1 pred W equals V means that vertex W was visited from V36. BFS and path finding 37 initialize all pred V to one record where you came from. Example adjacency list visited table, T/F, 0679243518 source 0 F1 F2 F3 F4 F5 F6 F7 F8 F9 F, pred Q equals initialize visited table, all files, initialize pred to 1 initialize to be empty 38. Example adjacency list visited table, T/F, 0679243518 source 0 F1 F2 T3 F4 F5 F6 F7 F8 F9 F, pred flag that 2 has been visited. Q equals 2 place source 2 on the queue. 39. Example adjacency list visited table, T/F, 80 F1 T2 T3 F4 T5 F6 F7 F8 T9 F7 6901524 neighbors, 2, 2, 2. Source pred marked neighbors as visited. Q equals 2 rightward arrow 8, 1. For record in pred that we came decu 2. From 2. Place all unvisited neighbors of 2 on the Q40. Example adjacency list visited table, T/F, 9800T1 T2 T3 F4 T5 F6 F7 F8 T9 T2 43517 neighbors 8 2, 2, 2 8 source pred Q equals 8, 1, 4 rightward arrow 1, 4, 0, 9 mark new visited neighbors. Record in pred that we came decu 8. From 8. Place all unvisited neighbors of 8 on the queue. 41 Notice that 2 is not placed on the queue again, it has been visited. Example adjacency list visited table, T/F, 0 T1 T2 T3 T4 T5 F6 F7 T8 T9 T neighbors 468023971582 to 12, 128 source pred Q equals 1, 4, 0, 9 rightward arrow 4, 0, 9, 3, 7 mark new visited neighbors. Record in pred that we came decu 1. From 1. Place all unvisited neighbors of 1 on the queue. 42 Only nodes 3 and 7 haven't been visited yet. Example adjacency list visited table, T/F, 0 T1 T2 T3 T4 T5 F6 F7 T8 T9 T2 351769804 neighbors 82 to 12, 128 source pred Q equals 4, 0, 9, 3, 7 rightward arrow 0, 9, 3, 7 decu 4. 4 has no unvisited neighbors. 43. Example adjacency list visited table, T/F, 00 T1 T2 T3 T4 T5 F6 F7 T8 T9 T2 4351768 neighbors 82 to 12, 128 source pred Q equals 0, 9, 3, 7 rightward arrow 9, 3, 7 decu 0. 0 has no unvisited neighbors. 44. Example adjacency list visited table, T/F, 90 T1 T2 T3 T4 T5 F6 F7 T8 T9 T2 3517680 neighbors 82 to 12, 128 source pred Q equals 9, 3, 7 rightward arrow 3, 7 decu 9. 9 has no unvisited neighbors. 45. Example adjacency list visited table, T/F, 0 T1 T2 T3 T4 T5 T6 F7 T8 T9 T8 2 to 1 2 3 to 1 2 8 source 4 1 7 6 9 8 0 2 3 neighbors 5 pred mark new visited vertex 5 Q equals 3 7 rightward arrow 7 5 record in pred decu 3 place neighbor 5 on the Q that we came from 3 46 example adjacency list visited table T/F 0 T1 T2 T3 T4 T5 T6 T7 T8 T9 T2 3 4 1 5 8 0 9 7 neighbors 6 8 2 to 1 2 3 7 1 2 8 source pred mark new visited vertex 6 Q equals 7 5 rightward arrow 5 6 record in pred decu 7 place neighbor 6 on the Q that we came from 7 47 example adjacency list visited table T/F 0 T1 T2 T3 T4 T5 T6 T7 T8 T9 T neighbors 2 4 3 1 7 6 9 8 0 5 8 2 to 1 2 3 7 1 2 8 source pred Q equals 5 6 rightward arrow 6 decu 5 no unvisited neighbors of 5 48 example adjacency list visited table T/F 0 T1 T2 T3 T4 T5 T6 T7 T8 T9 T neighbors 2 4 3 5 1 7 9 8 0 6 8 2 to 1 2 3 7 1 2 8 source pred Q equals 6 rightward arrow decu 6 no unvisited neighbors of 6 49 example adjacency list visited table T/F 0 6 7 9 2 4 3 5 1 8 source 0 T1 T2 T3 T4 T5 T6 T7 T8 T9 T8 2 to 1 2 3 7 1 2 8 pred Q equals pred now can be traced backward to report the path. Stop. Q is empty. 50. Path reporting nodes visited from 08122 to 314253677182998. Try some examples. Report path from S to V. Path 0, GT path 6, GT path 1, GT51. The path returned is the shortest from S to V. Minimum number of edges. BFS tree. The paths found by BFS is often drawn as a rooted tree, called BFS tree, with the starting vertex as the root of the tree. BFS tree for vertex S equals 2. Question: what would a level order traversal tell you? 52. How do we record the shortest distances? D, V, equals, D, S, equals 0, D, W, equals D, V, plus 1, 53. Application of BFS1. Application concerns how to find connected components in a graph. If a graph has more than one connected components, BFS builds a BFS forest, not just BFS tree. Each tree in the forest is a connected component. 54.